Hello and welcome to all participants of the SimScale workshop series on Formula One. A merry welcome from our side to everyone to the last session number 5. Today we'll be talking about nonlinear stress analysis, and to be a bit more concrete, we will talk about the valvetrain and things like camshaft, rocker arms, and valves. This is what you can see in this picture on the right. But nonlinear stress analysis is actually something that is much more prevalent than only in valves. Here on the left side you can also see another example of a piston, and this example very well also shows how nonlinear stresses are present in different parts of a Formula One engine. As usual, if you have any questions during the webinar, please use the chat function that the webinar client has. Enter your questions. We'll try to reply to them on the fly, or if there is a good occasion, we will just talk about the answer during the course of the session. Okay, now let's get started. As I said, this is session number 5 already, so today we'll conclude this workshop series finally. We had a very good time together with all of you during the last few weeks. We were really happy to see you work so actively on SimScale. There were many very, very good homework submissions, and we really had a lot of fun presenting and preparing all this to you guys. So I hope you're going to enjoy the last session of today. As already said, today we'll be talking about the stress analysis of a valve spring. So today we'll go deep inside the Formula One racing car, actually way down inside, so it's very hard to the engine. So first of all, let's talk about our agenda today. As usual, we'll take a look back at the homework from last week, just quickly. Then we'll present a few facts about Formula One engines, some fun facts, but also some more technical details. And the goal is that all of you finally, or that all of you understand how a Formula One engine works, which parts we have in there, what is so special about them, and then we will discuss a simulation, the simulation we've just been talking about, the valvetrain, how this can be simulated on SimScale. As usual, we'll talk about the results. What can I do with the results? What can I learn from the results of the simulation? And then there's going to be a final homework. As normal, we will describe this task at the end. And then, of course, there will be a few minutes left for Q&A, and then you can ask any questions related to today's topic or in general. Just a brief introduction. Who is talking to you now? My name is Johannes. Nice to meet all of you. I'm actually Director of Fluid Dynamics in SimScale. I was one of the guys presenting other topics in this workshop before, so some of you already know me. And next to me I have my colleague Richard. He's a senior engineer with SimScale, has been with us for a long time already, and he'll be the one to present the structural simulation on SimScale in a few minutes. But now I'll just give him the opportunity to present himself for a minute.
So hello everybody from my side today. I'm Richard. As Hannes introduced me, I'm senior engineer at SimScale. And yeah, I hope you have a fun time today and we learn something about valvetrain assemblies and how we really can use simulation to improve our engine design. So warm welcome from my side. You hear me in a minute when we go to the simulation part of this workshop today.
Okay, thank you, Richard, for the introduction. Now you know who's talking to you and who will be talking to you. So let's finally get started with our topic. Oh no, sorry, I forgot about the homework. Let's briefly take a quick look back at the homework from last week. Again, a big thank you to everyone who submitted his solution. There were really great submissions as usual. We were really stunned by what you guys achieved out there. We have one of the examples here on the right. There's a picture that shows you some of the eigen modes of our brake disc assembly. Yeah, it was really great to see all of your work. We had a good time answering all your questions and assisting some of you, but all in all, it was really a very nice experience. For the entire workshop series and also for the today's session, you will find more references and information at simscale.com/workshops. This session will be recorded as well as the other ones have been recorded before, and this video is going to be posted on YouTube, and the link will be published on this very workshop page. So if you want to watch it later, you can just go to YouTube and then find the video there. We have an FAQ section, as this was quite useful before. I'm just going to mention it again. So if you have a question that you feel is so well, basic that somebody else might have already asked us before, it's most likely already on the FAQ section. So please just take a look at this page. And we have a few tutorials in the documentation. That's another part of our SimScale ecosystem. We have a huge documentation where you find simulations explained in very much detail, step by step. And this really shows you everything that you need to know to set up the simulation. Okay, now I think is the time to get started. So let's talk about Formula One engines, or, well, to be more precise, let's talk about combustion engines or internal combustion engines before that, to make sure that everybody's on the same page about engines. So Formula One engines, they belong to the more general category of internal combustion engines. That means they consist of a few recognizable parts which are present in almost any car engine out there, at least these days. We are talking about four-stroke engines, and this is the first technical term here. A four-stroke engine means that an engine has four different steps that it performs in order to produce power. And these four steps are depicted here. So what you should do with these four pictures is you read them from left to right, and you have to imagine that this part here, this is actually called the crankshaft. This part is turning all the time, and while it turns, this part here, this is the piston, keeps moving up and down, and different things will happen during this movement. So let's just briefly talk about what is actually happening inside an internal combustion engine. So a few words. I already mentioned crankshaft. This is this part down here. This is the point where the engine actually releases its power to the outside, to the gearbox, for example. The power itself comes from up here, and this part, the silvery shining part here, is called piston, and this piston is moving up and down, as you can already see in those pictures. First of all, it starts with the so-called induction phase, or sometimes it's also called suction. So the engine sucks in a mixture of air and fuel, and what we see here, this bluish area here, is actually mostly air and contains a little bit of, well, say, petrol or any type of gasoline, which is already mixed in as a little, well, it actually as a spray. So you have little droplets of fuel in there. It gets sucked in because the piston is moving down. These two T-shaped pieces up here, there's one on the left and one on the right, are the valves. And these valves control the flux or the flow of our working fluid inside the engine. So in this state, when we suck in the mixture of air and fuel, we have the valve on the right, which is called the inlet valve, open, while the outlet valve, that's the one on the left, is closed. So I hope you can now imagine how this works. The piston moves down, air and fuel comes in from the right, goes around the inlet valve because it's open, but it cannot go out here because the outlet valve is closed. This is number one. So this is how the fuel and the air gets into the engine. The next stroke we have to talk about is the compression stroke. So what happens now is the inlet valve closes. This is actually not, well, it's barely visible from the pictures. That's why I'm telling you. So the inlet valve closes and the outlet valve stays closed. That means everything is now closed. The air and fuel mixture cannot go anywhere. And the piston is pushed up. And this pushing movement comes from the rotation of the crankshaft, which pushes the piston upwards. And this is why it's called compression. This air and fuel mixture gets compressed, its volume decreases, and its pressure increases. And you should already try to keep that in mind, because we'll be talking about this in a few minutes. Again, the pressure increases and the volume decreases. So pressure and volume, increase, decrease. I think you're getting the idea. So we're compressing this. Now the piston still has a little way to go up, and once it is all the way up, we ignite this mixture, because this mixture is actually, well, it can burn. As you know, fuel does burn when it is in contact with air, and then you just need a little spark to make it explode. And this part up here is called spark plug. This is the one that creates a little electrical spark by electrical discharge, basically. So we have a little spark here that will set the entire mixture on fire, and then you have some sort of, well, it's actually not an explosion. We should use the term combustion here. So you have a very rapid combustion going on here, which is, again, increases the temperature and also the pressure. So what we have now is a very tiny volume of super hot gas under very high pressure. And, well, I guess you can imagine what comes next. The crankshaft just turns a little further, and then it allows the piston to move down again. And when the piston can move down, it's actually being pushed downwards by this very hot gas that we have here. So the temperature and pressure are still very high. It pushes down the piston, and this is what creates the force, and in effect releases the power to the crankshaft, and then well, this is actually how the power goes outside. And then everything repeats all over. So once we've reached the point here, we will do another revolution. Actually, this should also be mentioned here. So it goes down, it expands. This is called expansion stroke. And then what do we have then? Once the piston has moved all the way down, the gas is still there, but now it's burnt. It's burnt fuel together with, well, whatever's remaining of the air. So it's probably mostly nitrogen and less oxygen than before, or almost no oxygen. What happens next is that the outlet valve, the one on the left, opens. It's actually, I think I did confuse a bit some of the pictures here, sorry. The valve on the left opens, and then we push out this burnt gas to our outlet valve. And then all this process actually repeats over again. So the next thing we do is this outlet valve closes, the inlet valve opens, and then we suck in new mixture. And yes, I'm very sorry, there was a remark which is correct. Picture 3 and 4 should actually be switched. So the picture on the far right should go on spot number 3, and this picture should move to the right. So thank you for that remark. We're going to fix this in the slides which are going to be published. Okay, so this is how an internal combustion engine works, basically. Now let's just talk about it one more time, but a bit more in a bit more detail. I just mentioned the concept of pressure and volume. We've seen that you can describe this gas or this air and fuel mixture with two parameters, namely pressure and volume. In this diagram, we plot the pressure over the volume. And with volume, I mean actually the volume that is enclosed between the piston and the valves and, well, the enclosing walls. So as we see, for example, as the piston moves upwards, it compresses the mixture, and this means the volume decreases, so we are traveling here along the x-axis to the left. So compression means we're actually traveling from right to left. So let's start with this compression stroke. When we started, we have our entire gas or combustion chamber filled with a mixture of fuel and air. So what we do then is both valves close and the piston moves upward and really squeezes it and compresses it to a very small volume. So the volume decreases, and as we decrease the volume, we increase the pressure. So we travel along this curve here in this direction indicated by the arrow. I hope you still remember the strokes. The next thing that comes is the combustion. So we have that little spark set off by the spark plug, and this will actually trigger the combustion, the spontaneous combustion of our air and fuel mixture, which means that the pressure and temperature rapidly increase. Really, that goes within a very small fraction of a second, very fast. So what we do next is we go up the pressure line with almost no change in volume, but we really go up very far in terms of pressure. So the pressure now is super high, and this is now ready to be released. So all this energy that we have now in this tiny volume of compressed and very hot gas is now ready to be released. And as we move down with our piston, the volume increases again. That's why we're traveling to the right, and the pressure decreases. And all this way down, we release the energy which has been stored in this gas. This is actually a very nice graphical representation because this graph readily shows you how much energy you are releasing within the process. Because whenever you have a plot of pressure over volume, you can integrate this mathematically, and the result will be work. So what we have in this graph is actually the amount of work that is being released during this expansion process. And this is basically the gray curve that we have here. So what I've been talking about just now is that we release this amount of energy while traveling down. And then once we've reached the right corner, the piston is all the way down, and now we have to change the gas. So what we have inside our combustion chamber now is just burnt fuel, a mixture of burnt fuel and air, and probably no oxygen. So we need to push that out. That needs to go into the exhaust and then basically into the environment. So the exhaust valve opens while the inlet valve stays closed, and when the exhaust valve opens, that means that the pressure which is felt by the gas is basically ambient pressure, so it's quite low. The pressure stays constant, and the piston just does one movement all the way up again while pushing out this burnt gas mixture. And then once the piston has moved all the way up again, we close the exhaust valve and we open the inlet valve, and this means we can suck in new air-fuel mixture. And this is what we do here by traveling to the right with almost no change in pressure, but with a large change in volume. So once we have reached this point, our entire combustion chamber is full with fresh air and fuel mixture, and this is ready to be compressed, and then we repeat the game all over again. I just briefly mentioned something about work. This graph nicely represents the work. So where now exactly is this tiny piece of work that we get released in every turn of the engine? Well, it's this dark gray area, because the energy being released during the expansion is everything that is below this curve. But we must not forget that there is some energy that we need to put into the process in order to compress the gas. And this is the energy which would be enclosed below this curve, this part of the curve. So we need to spend this amount of energy, which is, well, doesn't have any specific color, it's basically white, but we release this amount of energy. And in total, you can imagine that what we, in effect, release each cycle is this dark gray area. So this is all I was actually trying to say. I hope this made it a bit more clear what actually happens inside such an engine and the amount of work that is released each cycle. And this sort of explains us something about the behavior of energy release in an internal combustion engine. Because this, just suppose we're holding the throttle steady and we don't move it, we don't push it anymore. We just hold it steady in a certain place. That means that we're not changing the shape of this curve, but if we are having higher revolutions in this engine, this amount of energy is just going to be released more often. And this means that the energy, that the power output of the engine increases. So RPM basically is one factor in the power output of an engine. What also could we do in order to increase the output of our engine? Suppose the driver pushes the throttle a bit more. So that means we can suck in a bit more air, and also in order to keep the mixture ratio constant, we can also mix in a bit more fuel. And when we ignite this mixture, we will have higher temperatures and also higher pressures. So when the driver pushes down the throttle, it actually means that this part of the curve shifts upwards, and as we just discussed, the area between the area below this curve shows us how much work is being released in each stroke. So if we push down the throttle just a bit more, we raise this part of the curve and then also increase the area, and in turn increase the amount of work done in each engine revolution. Okay, so this is actually what I wanted to tell you about this. Now let's focus a bit more on Formula One before we move over to the simulation. What is so special about Formula One engines after all? There are actually very strict regulations on F1 engines. You cannot simply take any engine and put it into a Formula One car because the rules are really, really very strict. So let's just briefly talk about the details here. We have 6-cylinder engines, and these are normally configured, or these have to be configured in the V-type, in the so-called V-type engine, which means that we take these 6 cylinders and we arrange them in some sort of V shape, which you can recognize here in this picture on the right. The pistons or the cylinders are actually here. There's a bank on the left which has 3 cylinders, and there's another bank on the right which has also 3 cylinders, and they are arranged with a 90-degree bank angle. The displacement is 1.6 liters. Displacement is the total amount of volume that is that is actually being pushed or sucked with one full motion of the piston. And well, it even gets stricter than that. The bore, which is the diameter of the piston, is 80 millimeters. The stroke, that is the distance which is covered by the piston when it moves all the way up and all the way down, is 53 millimeters. Just another fun fact that we see here, the stroke is shorter than the bore. This means that the cylinders are actually, they have a comparatively large diameter, but they don't move that much. And the reason why we do that is that we have very high RPMs, very high revolution counts, and if the stroke would be too large, we would have very high piston velocities, and this in turn would increase the loads on our entire engine assembly so much. So what we do is, in order to achieve high RPMs, we have a larger bore but a smaller stroke. The maximum RPM are limited to 15,000. This is quite a lot already. If you get a high-performance motorbike, it will do about 10 to maybe 13,000. So this is again a bit above a motorbike. and or any sports bike. And as we said, we have 6 cylinders, so this is definitely a high-performance engine. And this is also the reason why the Formula One cars have this very distinct sound. The engine RPM are really high, and we have 6 cylinders, and all that makes this very unique and special sound of a Formula One car. The material is usually aluminum and iron-based alloys. Another word I wanted to say about this entire assembly. We have 6 cylinders, and they're arranged in this V shape. Now, if you take a look from above, we can see that we can actually assign numbers to those cylinders, and they are counted like this. So we have cylinder 1, 2, 3, 4, 5, 6, and we have a certain firing order, which is also mentioned here. So when we fire those cylinders, they do not all fire at the same time, but one at a time, and there's a certain order. I will not talk too much about this order, but it's basically, or the purpose behind this is to keep the engine vibrations low and to have a smooth delivery of torque or of engine power over the entire revolution of the crankshaft. Okay, now let's get a bit more specific. We'll be talking about valve design in this session. So let's just quickly take a look at these pictures to have a better understanding of an engine valve. The engine valve is a very crucial part in engine design because it has to keep the combustion chamber tight, so we must not lose any of the gas which should be enclosed there. But at the same time, they need to move very, very fast. So this is one example. Just take a look at the picture on the left. This is an engine valve which is open. So here, down here, this is the circular part here is the one that actually closes or encloses the gas. This grayish part up here, it's actually not entirely drawn correctly, but this is the cylinder head. So if we want to, for example, suck in new fresh gas fuel mixture, it has to go around the valve and then goes all the way through here, and then we have it in the combustion chamber. If we want to close the valve here on the right is closed, then, well, as I said, this is not drawn entirely correctly, but then this area basically closes, the valve touches the cylinder head, and then the gas cannot go outside. When you design an engine valve, there are 2 main problems you have to deal with. One is called valve float, and the other one is called valve bounce. We will see both of these problems later on in a few videos that we prepared when we did the simulation on SimScale, and you will see from those videos alone that you can have very severe engine damage if these 2 phenomena are not taken into account properly. Valve float is the situation when the valve train does not remain in contact with the camshaft. Maybe we should talk about the camshaft. What's the camshaft in the first place? Because we sort of skipped that. The camshaft is a part which is used to control the opening and closing of the valves. So let's just go back. Yeah, let's go back one picture. So the camshaft would sit here on top of the valves. Let's go back another few pictures, then we see it here in action. We have seen that the inlet valve here is on the right, the outlet valve is the one on the left, and the camshaft is this egg-shaped thing just on top. And this is just another shaft which also rotates, and as you can see, it's not fully symmetric, and as it rotates, it will push down the valve, and when you push down the valve, it opens it, and then if it turns a bit further, then it closes again. So this part here is the camshaft, and usually the camshaft rotates at half the speed of the crankshaft. Both of these are linked kinematically together, well, using gears or a belt drive. So when the crankshaft does one full revolution, then the camshaft will do half a revolution. And the reason for that is, since we have a 4-stroke engine, the crankshaft will do 2 rotations, but the valves only do 1 cycle. So that's why the camshaft RPM are actually half the crankshaft's RPM. Good. Now we've seen where the camshaft is. So if the valve train does not remain in contact with the camshaft, this is called valve float. Now, how can this happen? It usually happens at very high RPM. So if you have very high RPM, it can happen that when the valve is actually supposed to go up again, because the cam rotates a bit further, it is too slow and it sort of loses contact with the cam itself. We're going to see this very clearly in a video later when we talk about the results. Another problem that can occur when we have a wrong valve design is called valve bounce, and this is a partial reopening of the valve. Now, again, imagine we have the engine going at very high RPM. The valve goes up very fast because it needs to close very fast, and then it bounces against the cylinder head. And if this bounce is so intense, and you need to imagine that the cylinder and the valve itself, both are elastic structures. So this bounce, if this is a very hard bounce, then the valve might actually rebound from the cylinder head and then open again a little bit, and this is called valve bounce. And this is also a very bad operating condition for an internal combustion engine, because that means that the valve is not tight anymore and you have very high dynamic loads and very high stresses, and this is going to kill your engine very quickly. So these 2 conditions are something that we definitely don't want to have, and in a bit we'll see how to find this out using simulation. So this is finally the point when I want to hand over to my colleague Richard. He's going to show you a simulation of such a valve design where you can see the camshaft in action, the rocker arm, this part in the middle, and the valve, and you will see those different conditions. You will both see valve, both those conditions that I just mentioned, and then we have prepared some nice videos where you can actually see what happens at different engine RPM. So I'm just going to hand over the microphone to Richard, and we'll talk to you guys later.
Okay, so hello again from my side. Thanks, Hannes, for this great introduction. So I learned a lot about engines today, and so what we're doing now is we want to simulate somehow the dynamic behavior of part of the valve train assembly, and we want to take one design that we have built very roughly and see will this design be a valid design if we go to high RPMs or not, and if those effects like a valve bounce and valve float will appear or not. So that's what we're going to do today. First of all, we will upload the CAD model, or in this case we'll just use an existing project where the geometry is already updated, mesh it, and then set up the simulation, the dynamic nonlinear simulation, which is a very it's somehow some simulation type for experts, but we'll hope to explain to you today in a manner that you understand how to set it up and try to use it yourself when exploring the platform further. So then let's move to the platform, and in a second we're there. So okay, we're on the platform having the CAD geometry uploaded, and so let me first of all explain a little bit what we will see here. So we have 6 different solids, and the first part is here in red. It is the valve spring, and normally the valve is then attached to this spring, and when the rocker arm here pushes down, the valve is opened, and if the spring bounces back, the valve is closed. So, and the mechanism that steers all these opening and closing is mainly this crankshaft here, and this rotates with half the RPMs that the crankshaft does, and when it rotates, it pushes this roll upwards, and since we have here a rotation pin, we can move this other roll downwards, and it will press our spring down and will open the valve. So basically these are the 6 parts we're extracting now for the simulation. And the first thing we do is to mesh it on the platform. And for the meshing algorithm, we just used the simplest one we have. As you see here in the operation 1, we just used a full automatic tetralization of the geometry, which is a very automatic meshing, and you have to to do anything specific about the meshing. Just select if you want to have a fine or a coarse mesh. For this first demonstration, a coarse mesh would be sufficient, and you could also select to use a first or second order mesh. And for a detailed analysis, you would like to use a second order mesh to have a very good representation of the stresses also. And again, for today, we just used a first order mesh, which already gives you a good approximation of the results, all in all, but you have to be a little careful about the stresses. Okay, so this just takes a few minutes, and then we have the full mesh here. It looks okay for a first draft. We see the round areas are well preserved, and this is okay for a first simulation approach. So what we do now, I have already a pre-set up simulation, and what I do is just use a feature on the platform. I duplicate the simulation, and now I will go through it again and set it up again. So, okay. First of all, looking at the geometry, what we have here is an assembly of different parts. So what we have to take care is we somehow have to define the connections between those parts. And this is done via either contacts or physical contacts. At first sight, this might be a little confusing, but for contacts, we merely mean these are connections, and the physical contact means a contact that can close and open. So this is a highly nonlinear phenomena, which we really need a special solving algorithm to solve that correctly. But what we first do when setting up the simulation, we have to first of all choose the analysis type. So in the first sessions you did a lot of fluid dynamics. Last time we already did frequency analysis, and for this time we use a dynamic analysis. As this is a highly nonlinear analysis, I would switch to the solver perspective and choose from our different solvers the CAD solver. It is very good adapted to highly nonlinear phenomena, and we have a lot more options there than for the CCX solver, where you could also do a dynamically nonlinear analysis. For this case today, we have chosen the CAD analysis type. Okay, then what we first set up in almost any simulation we do are the different sets we have to use later. So normally, of course, for any boundary condition or load, as you already know, you can use either directly the phases or volumes, or you can beforehand create sets of the significant phases, which will ease later the assignment of boundary conditions. So we created some sets already. For example, for the contact pairs, we have here this first role, and we have always for a contact a slave and a master contact pair. And here for this role and the cam, which is actually this part, we chosen the role outer surface as the slave and the cam outer surface as the master. And there we can go through all the faces we have. This is the glue of the putting together of this role here and the rocker arm. And when we hide it, we can see, let's go to surface view, we can see that this face is the master for this roller pin contact. Okay, and there we have a lot of other surfaces defined where we'll have a look at when we go through the specific definitions. So first of all, what we do is we just glue parts together which are supposed to not really slip along each other or have a separation to each other. So I think whenever there's questions, we'll try to answer them, and there's a very good question now. The question is, where do I know which of the two surfaces that are in contact are the master and which are the slave? So this is a good question. So generally speaking, if you have physical contact or any contact set that is that has a slave and a master, it normally means that the degrees of freedom of the slave are somehow connected to the master. And normally, if you have a very good resolution of the contact, you use as the slave surface the surface which has a higher mesh density, so which has more elements over the surface. And if you have, for example, like on this side here, you have a very curved surface and you have a very straight surface, then you will anytime use the curved surface as the slave and the straight one as the master, because there you get the best approximation of the contact of the surface normals. And let's have a look what we did here. This is the contact roll 2 and spring, and let's have a quick look at the master entity. We select the assignment, we'll see, okay, this is correct. We did here for the master use the top of the spring surface, which is correct, and for the slave we used the more curved surface, which is the outer surface of the roll. Okay, so then we go through the setup. So what we first do is we simply attach the rolls to the rocker arm, because we do not suspect a lot of sliding there, because we already have a physical contact here, and since we do not want to introduce any friction, it should not change the results of our simulation if we fix it or let it be rolling free around the pin. So what we do here, if we then first hide the roll, I think this is roll 2, yeah. We select the assignment, we see, okay, as master entity, this is the pin outer surface, and let's go the other way around, hide the rocker arm, and have a look at the slave surface. There we see we selected the inner surface of this roll. So, and as a type of the contact, we can select a bonded and a sliding. And we have chosen a bonded one. We could also choose a sliding one. You have just to keep in mind that these contacts are linear contacts and rather connections than contacts. So the parts are in a defined state. They cannot separate or come in contact to each other. Either they're in contact all the time or they are not. Okay, so the same we do for the pin, and of course the mesh, we selected the CAM assembly mesh that we computed beforehand. One very important setting when you go to the model is we set the geometric linearity to nonlinear. So what you will have here is a rotating cam which goes through a large rotation. So therefore we need a nonlinear geometry representation. So you have to keep in mind whenever you have large rotations or large strains, you would need geometric nonlinear representation of the stresses and strains, and therefore you select here a geometrically nonlinear model. So that we did here. Then we go to the physical contact. So physical contacts, these are really the highly demanding ones, where the two parts can separate and come into contact again with each other. Here we have also a lot of settings which you can play around with, but you don't have to. Normally the initial settings are okay. I think that the standard contact would be the penalty method, which if you select one specific zone, would give you, let's have a look at the frictionless penalty, the penalty coefficient. This is the only parameter you really have to care about, and so the penalty coefficient normally should be in the range of the stiffness of the materials that come into contact. But here we have chosen an augmented Lagrange contact, which has one parameter, but it doesn't change at all the results, or shouldn't, so you do not have to touch it at all. So therefore you just, if you want to add a contact, add one and select the master and the slave surfaces and save it. So that's nothing you really have to worry about here. Then we go to the materials. So as physical contacts, we define three ones. So first of all, here again, the cam and the roller, then the spring and the other roll, and the third one is the pin of this rocker arm to the rocker. Okay? Then as materials, we have just chosen the standard steel because we simply do not have any material properties, and also the springs are mostly different. It's a steel alloy and has not highly different stiffness parameters than this standard steel has. Okay, then let's go to the boundary conditions. We just used 4 boundary conditions to define the whole process. So first of all, we just fixed the pin of the rocker arm here in all 3 directions. So to have it fixed, then the same we do with the base of the spring, except that for the Z direction, which goes upward, we move it a little at the top in the first time step, just to simulate the pre-stress that the spring has. So normally, if you assemble the valvetrain, you have to pre-stress the valve spring, and this we simulate by just putting a little displacement here at the beginning, which we obviously do with the formula, which is possible here. You can use formulas and put their parameters x, y, z, or the time in there. Okay, the same functionality we use for the crankshaft rotation. So for these outer faces, which are connected to the crankshaft, we specify a defined rotation. This is mainly taking the rotation matrix and putting the values here into the formula. So this is a little math you have to take, but it's not that complex as it looks like. So in the last boundary condition that we have to apply here is the sliding of the spring top face. So the side faces, because normally the spring is inside a defined borehole where you can move upwards or downwards. So this is why we pre-described X and Y displacement, but we let it be unconstrained in the vertical Z coordinate. And basically that's it. What we do have to care about is not that much the numerical properties, could be just the initial ones that are chosen, but the time step definition. So what we have chosen here is a rotation, a camshaft rotation of 6,000 RPMs, which would mean that in 10 milliseconds we have one rotation. So we set this total simulation interval to 10 milliseconds and have a time step length so that we subdivide our total transient process into little time steps to capture the motion really good. And that's it. We used a high number of computing cores because this is highly nonlinear and we have to compute a lot of time steps so that we get the solution very quick. And basically that's it. What we also can do with the Cholestair solver, we could do some calculations at a few specific areas. For example, one of them is the top phase of the spring. We really want to know, we're really interested in the vertical displacement when the crankshaft rotates. So this we'll see later how this evolves. And basically that's it. We create a simulation run and we have let it run and have a look at the results. So we go to the post-processor. Of course, this will really take a few minutes to compute, or rather an hour, and go to the results. Yes, for the 6,000 RPM, we see something interesting if you have a look at this one, the max displacement at the spring top. What we see is it just has the correct motion, or resembles to be, but then it smashes against the roller and it tips off again. So this is what we see here in this graphics. If you can imagine it, we see a valve bounce. So we really see the bouncing here, and what is happening here is the valve is opening again. So I prepared some what I find cool videos to see the total behavior of the spring. So yes, so let's have a look at the stresses. So what we do is we we have 6,000 RPMs rotation velocity of the camshaft. That means we were in the range of 12,000 RPM of the crankshaft, so 6,000 RPM of the camshaft. And what happens is, if we move along here, we see, bam, there we have the detachment between the roller and the spring top, and again the bouncing back now here where the valve opens again. So what we see here is really a design that is not fit for this high rotational velocities. So we did the same simulation just with 3,000 RPM and have a look at the results here. What we see here is a clear non-detachment of the valve and the roller here, and this is an operating condition where we would say, okay, the valve should work for this rotational speed, but not for higher speeds. Okay, so let's go back to our presentation. So have a quick recap since we see the time is running. What we've shown is just the geometry upload. We haven't shown it, but it's very easy. We used the step file to upload it, and we created an automatic mesh of it, automatic tetrahedralization, which is very easy to set up. Just set how coarse or how fine the mesh should be, and that's it. It meshes assemblies, multiple parts at once, and what we have left out for today is just the preparation of the geometry and leaving out unnecessary details or parts, and mesh refinement. So normally if you really would have a high accuracy of the results, you will try to refine the mesh at least at those areas where you have contact and where you would see high stresses appear. Then for the simulation, we quickly skimmed through the process of setting the simulation up, have shown some boundary conditions and setup of the contacts. What we left out is material and numerical damping, which is somehow critical in dynamic simulations. But all these advanced topics you have seen here so far that were labeled advanced topics are then surely be talked about in the professional trainings that some of you will eventually take part in, as we'll come to it later. All of you who completed all of the homeworks will get an invitation to a professional training where we all go through also these advanced topics. Yes, we didn't have time for the post-processing online now, but we have seen the videos of the behavior of the spring and seen that it behaves not as we would like our design to be. So as we have the result interpretation for the 3000 RPMs of the camshaft, you have a very good behavior. You see that all parts remain in contact all the time. This is a very good sign. But if you go to the results of the 6000 RPM simulation, we see a detachment of the spring top face and the roller, which means we have a valve floating and again coming back up the spring and bouncing back. We also have shown in the video a valve bounce, which is really not what we want to have, because we risk a really heavy engine breakdown. And of course we lose power if the valve opens where it not should be open. And this is a comparison of the top movement of the spring, where we clearly see that for the 3000 RPM we're really good in contact with the roller, and we go down to a steady state where we do not have any vibrations. And for the other higher rotational speed, we have at this point a hard bounce back and the valve is opening again, and this is not what we want to see. And again, here on this side we see a valve float, so the rocker arm and the spring are detaching. Okay, so what I initially wanted to show you is that this design especially is not suited for high RPMs, and this is why the modern F1 engines do not have only those spring valves, but they have pneumatic valves that the opening is also steered by a pneumatic process which ensures that all the parts remain in contact, and yes, we get the maximum power of our engine. Okay. Then, of course, also for this webinar workshop, we prepared a homework which you can look up at our workshops page. So we have two levels again. One is a simple crankshaft part where you will fix two sides, one with the ball bearing and the other with the journal bearing. These types of bearing conditions are boundary conditions that you can have a look at the CAD stair solver when you choose the type remote displacement. So you would then, as the point, choose here the center point of this face, and then you can select the rotational degrees of freedom you want to let free or not, and also the displacements. They are like explained in this picture. And what you would also then do there is have a vertical force applied, which should simulate the pressure that is pushed on the cylinder head top. And in the level 2, you really try to do the whole assembly of the crankshaft the connection rod and the cylinder head with the real pressure that is appearing at the maximum combustion, and there you will hopefully, if you do both simulations, can say something about if we really need to model all the whole assembly, or we just can do the simpler model on the left to have a right estimate of the stresses, for example, inside the bearing. Okay, you will find the project on our workshop page, and you can import it directly and start simulating. So thanks again for today. I hope you have learned a lot, and I will give the microphone back to
Okay, thank you, Richard, for showing us the simulation. I guess this one is a rather challenging one, so it was good that we covered this in a bit more detail than usually. Especially the part about context was really important. I was just skimming through the questions. There was one question regarding which CAD modeler are you using to prepare your geometry. It doesn't really matter. You can use almost any CAD program which is out there. But once you are uploading the part, you should better use the step format, which is supported by most CAD programs out there. But other than that, it does not really matter which one you use. Okay, so thank you, Richard, again for this simulation. Let's just move over. So this is the Q&A slide. If any of you have questions, you can just post them now into the chat, and I will just give you answers as long as the questions are coming along. Okay. Good. So while you are typing your questions, we wanted to say thank you so much, because this is the final session that we had. This concludes our workshop series. Thank you for staying with us all the time. We had a really great time together with all of you, because we really, well, we were in contact a lot with some of you guys out there. We've seen extraordinary homeworks. Those were really great achievements by you. We were happy to see so many young engineers, so many really good engineers who really took the challenge and really did a great job in simulating all this. We have made a few promises in the beginning of the workshop, and we will keep them. So we had. We said that you will receive a certificate for taking part in this workshop series, so we're going to send them a bit later on. Some of you, actually, the ones who successfully submitted all the homeworks, are eligible for a professional training, and this is really a goodie which I think is definitely worth it. So you will be special guests who are invited to take part in our trainings. You can go to simscale.com/training to see what you can expect from such a training. It's really good. It shows you lots of different types of simulation. It gives you a nice introduction on very different topics. And if you have undergone such a training successfully, you'll have learned quite a bit about simulation in general, and also should be able to use SimScale to, well, solve many of your everyday engineering problems. We know that there are many students who have taken part in this workshop series, and we're particularly proud and fond of our students, having so many students on the platform. And this is why I'm specifically talking about our academic program. That means that every student out there can use SimScale free of charge. And this is really something that I cannot stress enough. All of you guys who are still students may use SimScale free of charge. That means you can simply register and say, hello, I'm a student, and that gives you unlimited access to all the features, and basically that is how you can continue using SimScale even after this workshop. And well, as I just said, thank you guys. I'm seeing a few very encouraging comments over the chat. So people say thank you to us, and we do the same. We say thank you to all of you guys for taking part. This was really cool. Yes, thank you. There are people saying thank you all the time. It's really cool. We're really happy to have so many people on board. And yeah, people say, oh, wow, this is really overwhelming, the comments. People say thank you all for such a great experience. People who are wanting to work in motorsports in the future. So I hope this was something that is going to be useful for you in the future. And yeah, you will hear back from us. As usual, we will post everything that is related to these sessions on our workshops page. And whenever, the invitations to our professional training, well, actually there's a question for that. Somebody is asking, how do you know if your homework assignments were accepted? We will send out invitations for this professional training in a bit, so it's going to take a while to take a look at all your submissions, but we will do that because you've spent such a lot of work and efforts on everything, and now it's our turn. We have to spend some efforts to take a look at all your simulations. This is going to take some time, and once we have identified those who submitted everything successfully, we're going to send out the invitations to our professional training. So just stay tuned and you'll hear back from us in a while. Okay, so thank you again. People are still saying thank you, and I must say I'm really happy to hear all that. Stay tuned, stay with SimScale. We will have more of these workshop sessions in the future on different topics. Just make sure you're following us on social media. We have a Facebook account, we have a Twitter account, we are on YouTube, so whenever there is new exciting stuff happening from us, you will hear as long as you do follow us on those channels. So I'm hoping to see many of you guys again in one of our next workshops or trainings, and till then I wish you happy time simulating, much success regardless of where professional success or success in simulating in general, and I'm hoping to hear back from you guys again. And thank you again. So you'll hear back from us once we are done with the grading of your homework. So thank you from Johannes and Richard. Thank you from SimScale, and have a nice day. Bye.